Hello, everybody. We are now at 5.3, the fundamental theorem of calculus. That's a pretty impressive title for a section, right? And it is, and it should be, because the fundamental theorem of calculus, as the name indicates, is absolutely fundamental to the study of calculus. That is, differential and integral calculus. And in fact, this theorem combines both of these in a very, very integral fashion. No pun intended. So let's take a look at this, one of the crowning achievements of the history of mathematics, the fundamental theorem of calculus, parts 1 and 2 in section 5.3. All right, so a good starting point to introduce to you the fundamental theorem of calculus is the average value of f over a over the interval AB, which we talked about before. Okay, so what is the average value of the function? If f is like this, you know, from f of a to f of b, it goes from this point to this point, goes up and down, in this case, down and up, and then down again. What's the average value? You know, if f is the temperature between the time A and time B, what is the average temperature? Or if f is the speed as you travel from t is equal to A to B, what's the average speed? And the idea is pretty simple. You take this the area, you know, again, think of this as like a sand or something, and then you kind of shake it, you know, just kind of shake it. And then eventually the sand is going to settle at some point here. And now this is the point where, you know, the excess sand will fill this part here and then just becomes a flat kind of thing, right? And so this is called F average, FAV, or F average, the average value of F. And I said the way we want this is we want that the integral, which is of course the area of this region under the curve between A and B, this should be the amount of sand, which is equal to F average times B minus A, because that's just the area of the rectangle, right? So from this, we found that the average F happens to be 1 over B minus A times the integral, right? So this is actually, it's very much like, you know, the average of a finite number of numbers. What do you do when you have a finite, you know, if I give you like a set of 6 numbers, what do you do to find the average? You add them up and then you divide by the number of numbers you have. And so it is very similar to that. And this is how we define the average. Maybe I should just write down that concept here, okay? So this is called the average value of f on the interval a, b. All right, the reason I am talking about this is because before I can define and prove to you the fundamental theorem of calculus, which by the way is going to let you evaluate the integrals in a fashion much more efficient than the limit of Riemann sums. Before that, I have to tell you a previous or a theorem that is a precursor to the fundamental theorem of calculus, and that's called the mean value theorem. No, not quite. The mean value theorem for integrals. We already had the mean value theorem, right? So the mean value theorem for integrals, what does it say? It says the following: if f is continuous, as usual. Now remember, for the integral to exist, the function doesn't have to be continuous, as we mentioned before. But if f is continuous, then there is at least one point. You can just say there is a point, but to be more precise, I would say there is at least one point C on this interval such that f of C is the average value of f. And that means this is an equivalent statement. There exists a point C such that at f of C, the value is going to be the average value of f between a and b. Said another way, so that would be the same as the integral, of course, is the length or the height of this rectangle, which I showed you right here, right? Which is f of c times b minus a. All right, so we are basically saying that if f is continuous, there is a point c so that f of c is the average. In other words, in this interval a, b, f is going to achieve the average value at some point, okay? Here's a quick proof of that to convince you that this is true. By the extreme value theorem, remember that's the one that guarantees the maximum and the minimum value for any continuous function on a closed and bounded interval. By the extreme value theorem, f has an absolute maximum, let's call that m, and an absolute minimum, which let's call that lowercase m, on the closed and bounded interval AB. That is to say, lowercase m less than or equal to f of x, less than or equal to capital M for all x on AB. Okay, so I can multiply all of these by b minus a, which is a positive number. Oh, you know what? Let's not do that. What I'm going to do is to use that statement that I stated a few, in the last section, to say that m, lowercase m times b minus a, that would be like the smaller, you have this m and then capital M and functions like this. This thing is the area of the smaller rectangle, and that's going to be less than or equal to the integral, which is the area under the curve, which is less than or equal to capital M times and the interval b minus a, which is to say that this integral is going to be between this small rectangle and this big rectangle. Right? This is sort of like the sandwich theorem or the squeeze theorem. Okay. Well, so that means you have the lowercase m, you're dividing each term by b minus a. And of course, the middle one now, this is exactly what we mean by the average, right? And so that is the average. Oops, that is f average. All right, so where do I go from here? Well, this, as you know, okay, this is a what we have is the lowercase m here, capital M functions kind of going like this. This is the minimum, this is the maximum, m is the maximum, lowercase m is the minimum, something like this, right? Well, lowercase m and capital M are both like, values on the y-axis. And remember, we have the mean value theorem, which is true for all continuous functions. Basically, if you pick any point here, any point between these two m's, lower and capital M, you have a point c, so that f of c is that the mean value, the intermediate value, right? So that's the intermediate value. And so that's what we will be calling that. So let's use that to state that by the by the intermediate value theorem, there is a c, at least one c on AB, such that f of c is this intermediate value between lowercase m and the capital M. And that's it. Okay, that is what the statement of the proof indicates. Right. So f of c, there is a point c, so that f of c is the average value of f on AB. And that completes the proof of this statement. All right, so this is just a preparation for the big topic of the section, which is, of course, the fundamental theorem of calculus. All right, so now let's, with this as a background, or with that said, let us consider a function f, which is non-negative on this interval from a to b as usual. Okay, so the function is defined on a to b, and it is continuous, and it kind of goes like this, whatever, right? We're trying to find this area a under the curve, right? And here's what we're going to do. This is something very different, right? Now, consider a function, not f, a new function that comes from f. Consider a new function, which we will call this capital A of x. All right, and watch what happens here. What I am going to do is to define this, for each x in, on this interval. I am going to define capital A of x to be the area under the curve of f between a and x. Now, this x can go back and forth, of course, right? So we are trying to find the area to the left of x under f. So the limits will be a to x, and this is the variable. I know it's different. So now, normally, we will write f of x dx, but because I'm using x here as the independent variable, I don't want to use the same variable. In fact, I should not, and I can't. All right, so I'm going to use another variable, f of t dt. Now, this is called a dummy variable. Not that it's stupid, but it's it could be anything. All right, so this is the new function, which as x moves to the right, it's going to get bigger and bigger because the area gets bigger. The area indicated or shaded in red is going to get bigger and bigger. So a is an increasing function. Note, oh, maybe I should say this. Yeah, so this is the area under f on not a to b, but a to x, right? Note here, capital A of a is, of course, the integral from a to a, so that's going to be 0. And capital A of b is the integral from a to b, so that would be the whole area, right? This is the definite integral that we are interested in finding eventually. All right, now here's a question. The question is not, what is the formula for A yet? Okay, that's part 2, or the second part of the fundamental theorem, how to evaluate this. The question before that is, how fast is A increasing? I told you A is an increasing function because, as the picture shows, as x increases, the area to the left of f increases. So what we are trying to find is this, the derivative of A, the derivative of the area function. Okay, all right, let's now follow this carefully because I think it's very important for you to try to understand this. All right, so what we are trying to do is to find d dx of A, or you can just write this as A prime with respect to x, right? And that, of course, is the limit as h approaches 0 of, sounds familiar, right? This is going to be A of x plus h minus A of x. And that's the limit as h approaches infinity of, the denominator is h. What is the numerator? It goes from, it is integral from a to x plus h of ft dt minus the integral from a to x of ft dt. Now, what kind of area is this? So you have this x in here and x plus h is here. And notice here, this expression is the area to the left of x plus h. So that's all of these. Okay, but then from there you subtract the area to the left of x. So we subtract this. What's left here is this, the area of this little sliver. And I say sliver because eventually we're going to let h approaches x, right? So that's the numerator of this. This is very important for you to understand that part. So you can rewrite this as the limit as h approaches 0 of 1 over h. And let's go ahead and write down this other part here. That part is going to be the area from x to x plus h of ft dt, which is the limit as h approaches 0 of 1 over h times the, well, actually, let's go ahead and look at this really carefully. You know what is happening here? If you look really carefully here, even if you don't look really carefully, you know what this is? That looks very much like the average value of f between x and x plus h, right? I mean, let's look at this. The average value of the f between x and x plus h would be the integral, basically the area under this curve, f, in this interval divided by the length of this interval, which we used to call, b minus a, but it's this minus that, which of course is h. So this is the average value of f. Okay, so this is the limit of f. That, let's go ahead and write this down. Limit the limit of the average value of f on this interval from x to x plus h. That's what we are trying to find out. Now, by the mean value theorem for integrals, which we just talked about a few minutes ago, there is c on this sliver, on this very small interval from x to x plus h, such that f of c is equal to the average. Let me go ahead and write this. So that f of c is 1 over h integral from x to x plus h ft dt. Okay, well, I think you can see what's happening here. As h approaches 0, now notice here, c is somewhere in here, right? So c is somewhere between x and x plus h. And as x plus h approaches x, there's really no difference between x and x plus h. It gets smaller and smaller, and c is squeezed between x and x plus h, and ultimately just becomes x, right? So then we say f of x is this limit, which of course is the thing that we were looking for. And what was this limit? This limit actually was that equal to this. This is what we were looking for, right? The limit we were looking for is a prime of c. Okay, so what is it saying? It's saying that the derivative of ax, the area function, turns out to be f of x. Now remember what a was. A is the area of under f between a and x, right? And does it make sense? Let's think about this. How fast is this area changing? Well, maybe I'll give you another picture here. I mean, this is very, very important. Okay, so maybe I should even write this. d dx of the integral from a to x of ft dt turns out to be f of x. That is the original function, all right? And I will interpret this. I will write a couple of interpretations of this. I can't emphasize how important this is. And essentially, this is the statement of the fundamental theorem of calculus part 1. But here's what this says, okay? And I think you can verify this. I think you can understand the statement by saying this. Let's say f, it goes really small here and gets really up here like this. All right. So when f is small, okay, f is f of x is kind of small here. As x moves a little bit, just tiny amount by in like 0.1 units to the right, the area changes only by this much, right? But when when f of x is really big, by moving this slightly to the right, you're actually adding a lot to the area. So what this is saying is that this area function changes at the rate which is exactly f of x. And that should make sense because again, here, the rate of change is small. Here, the rate of change is big. Why? Because f of x is big here and f of x is small here. So this is intuitively, not too difficult to understand. Now, that is what this statement says, right? So let's try to understand what this says. I mean, this picture is one way to understand this. This is saying that the derivative of the integration function, or the derivative of the integral of f, is f itself. Okay, so in other words, if you start with f, and if you are going to take the integral of f, and if you take the derivative of f, you get the same thing back. So it's almost like, maybe I should write it this way. You start with f, and how do you integrate this? Well, you just take the integration. So you take the, you take the integral of a to the x like this, f dt. This process is the integration. But if you differentiate the integral function, then you get the original f back. So essentially, this is saying differentiation. Listen very carefully. I'm about to make one of the most important statements in calculus, maybe the most remarkable, most profound, most thought-provoking, most amazing statements. One of the most amazing statements in all of calculus, which really basically is the central thought or idea or statement or theorem on calculus, right? Differentiation and integration are opposite procedures. So over here, I said, so here's the integration, right? So when you try to integrate f and differentiate the integral function, you get the original function. That, my friend, is the fundamental theorem of calculus part 1. I didn't write that yet, so let me go ahead and formally write that. And because it's so powerful, so important, so royal, if you would like, if you please, so I'm going to use the purple ink, okay, to state that. And in fact, that's what I did over here too. I used this purple to write the section number and the title because it's royal. It's worth writing in purple. All right, so what does it say? The fundamental theorem of calculus. Now there is a second part. So I'm going to call this the fundamental theorem of calculus part 1. Okay, there is a part 2 coming, which is also extremely, extremely wonderful. All right, this one says the derivative of this area function from a to x of f t dt is equal to f of x. The derivative of the area function, i.e. the derivative of the integral function, is f itself, which means that the differentiation process and the integration process are inverse operations or opposite of each other. Okay, so that is the fundamental theorem of calculus part 1. It is theoretical, all right, and this is good to know. But when most people talk about the fundamental theorem of calculus, they're actually referring to the second part, which I am about to go into. All right, so what can you say about this? And so the second part is what I'm going to tell you on the second part of this video on section 5.3.